That's old money. For a self-replicating machine and a stamp addressed envelope. So I sent it away, postal report by my mother. And a series of cardboard cutouts arrived. But they were incredibly clever because you put them in a frame and you shook it. And when you made a pattern of the cardboard cutouts, it would recruit more cardboard cutouts to replicate the pattern. So it really was a self-replicating machine made out of code. Been fascinated by self-replicating machines ever since. So when 3D printers came along, I thought, finally we've got a manufacturing technology that stands half a chance of copying itself. So I set up the RepRap project to do precisely that, make a 3D printer that copied itself. Didn't know if it's going to work or not, but it turned out to work. So here we are. That's the brief history.
Amazing. You love it. That's ready to
Here
go.
we go. Right, yes. Julia asked me for a title, which was, the trouble with picking a title is when you don't know what you're going to say, you've got to find a title which might allow you to say anything. So the difficulty was compounded by the fact that the project I actually want to talk about was slightly secret at the time because we hadn't published any papers on it or anything. So anyway, I told her printing electronics, which is approximately the thing that I'm going to talk about, but I put a knot in front of it in brackets there, just so that you don't all throw old fruit at me when it turns out not quite to be about what you might be expecting. Anyway, 12 years or so ago, I retired to a life of leisure. A life of leisure seems to consist of working for 3 different organizations. Well, 4, if you count the 2 things I do for MIT, only one of which they pay me for. Being fairly busy. Anyway, let me tell you about the team involved in the project, which I'm going to tell you about today. This is actually a project that was not instigated by me. It's instigated by Neil Gershenfeld, whom many of you will have heard of. He runs the Center for Bits and Atoms at MIT, and in fact, that's the location of the project. And then the other 4 people on the right there are the people who are basically his research assistants. And I have to say, having been a reasonably senior academic myself and applying for research grants and so on, it's very convivial to find yourself back in the role of being a research assistant with no responsibilities whatsoever. So that was quite an interesting start. I should say that the entire thing is funded by UK's ARIA agency. They put the money in. So we've got this interesting thing of a Boston University being funded by the UK taxpayer to do a project involving one UK national, which may be the reason he asked me to live on such good established. Anyways, there we go. The actual project is called Physically can't even say the name of my own damn project. Physically Reconfigurable Computing, Learning How to Learn. What we're trying to make is computing systems that are mechanically able to reconfigure themselves. And what we want to do with them is to build a neural network, an artificial learning system that doesn't just learn, but learns how to learn. In other words, it learns how to reconfigure itself to make itself work better. Now, we're a long way off from that goal, as you'll discover when you get to the end of this talk. But nonetheless, I'm going to show you some of the steps we've taken on the route towards that. Okay, so we're going to be, talking about, as I said, not printing electronics or printing electronics. We already print electronics. This is the sort of they're called printed circuit boards, for heaven's sake. So just going backwards from the bottom right, here's a conventional piece of electronic construction. Bottom right is radiator controller, Wi-Fi radiator controller designed by my daughter and me as part of our central heating system. On the left is the core PCB that uses an ESP32 to talk to the Wi-Fi. Up top right there is the actual PCB design out of, are we KiCad or KiCad? Does anyone like KiCad? Votes for KiCad. Votes for KiCad. Right, okay, KiCad it is. The PCB design in KiCad and then schematic on the left. Now, what we'd like to do is to eliminate the bottom right on the bottom left and the top right thing altogether and just go straight from the circuit diagram that we've laboriously created and generate something automatically out of it that works. Okay, well, we're all familiar with the idea of standard electronic components. They look like the stuff on the top. 20 years ago, they used to, more than that probably, they used to look like stuff at the bottom. And these are all standard shapes. There are very precise definitions of them, defined in inches, heaven help us, for how their dimensions are organized. You'd think that that would be enough standardization. But actually what we want to do is to escape the traps of this wide variety of different standards that we have to deal with. And we'll come to that in a second. And these things aren't always standard. There's a fabulous online resource called Cursed Footprint, where they show you pieces of electronics, which when you look at them, you think, I am not going to design with that thing. Doesn't matter how close it is to having the functionality I want. Just look at the PCB I'm going to have to make it work, and look at the way the solder's going to migrate when we try and put the whole thing together. Anyway, the Cussy particularly egregious example. There are a whole load of them. So even when you've got standards, people abuse those standards. So let's have a list of desiderata. And there's an extra one that I'm going to add to this. We want one standard shape for everything. Doesn't matter if it's a billion transistor microcontroller or a single resistor. We're going to have one standard shape for everything. We're going to put those shapes together in 3 dimensions. The big problem with printed circuit boards is lack of dimensionality. Sure, you can route tracks over each other if you've got a double-sided board or a full-layer board or whatever, but it's a real pain to be restricted to 2 dimensions. Apart from anything else, it doesn't give you enough versatility in the shapes that you can make to fit it into other objects. So we're going to have everything working in 3D. Ideally, we don't want to do any soldering, though we might not be able to meet that requirement. And we want it to be completely robotic from schematic to product. And we want it to be scalable. We want to be able to use it to build a single transistor amplifier, and we want to use it to be able to build a GPU so we can talk to it. And it will talk back to us. And as I mentioned in the very first slide, we want to build an AI that designs and modifies its own successor. We're a long way off from that. We have not done it. That we trail the end of this talk as being a disappointment. So, okay. We start off with something that actually, this is from Cornell, but it actually started at MIT and then Pod Lipson at Cornell took it over. A project called BitBlocks. And what we've got here is a series of 3D printed objects combined with printed circuit boards that plug together in the manner that you can see. And you can arrange the wire to each other. You can arrange components on them. So, for example, bottom left here, we've got an LED on one of these things. And they're all the same size and shape. And you can indeed put them together in 3D. And that's pretty much what we're going to try and do. That we're going to make a simplification of this and then go back to it in terms of complexity, which you'll see at the moment. Okay. A modification of this idea is DICE, Discrete Integrated Circuit Electronics, which was the precursor to this project at MIT. Similar sort of idea. We've got chips mounted on standard carriers that will go together in 3-dimensional shapes to build electronic circuits. That works, and you can build things with it, but the actual objects themselves are a little bit laborious to construct. We'll come back to that point in a minute as well. Okay, here's the robot that puts those together, or rather the head of the robot that puts those together. It's a thing that picks them up from the right there and assembles them onto the little carrier on the left, and you can build electronic circuits in it entirely automatically. Let's simplify things by saying we'll get rid of all those connectors and the fancy shapes. Let's instead just have little squares, okay? And those little squares are going to go together in a packet of pillars, which are the light brown objects you can see on the top of the picture there. And the little squares will have components on. And in the nature of squares, they'll have 4 corners or perhaps 8 connectors, 4 at the top, 4 at the bottom. So people will separate those out with a 2-sided PCB. And we'll make these using PCB technology. And at the bottom right, you can see a simple circuit assembled using this sort of idea. And this kind of works. And it's very easy to make these things because we're really, by we, I mean human beings, are really good at making printed circuit boards. Boy, can we make we make a lot of printed circuits. We make them very quickly. So we've got really good technology there. And that brings me to the point that I left off the slide, which I wanted to mention, which is recycling. Electronics is some of the most hard to recycle stuff that human beings make. In particular, fiberglass printed circuit boards. Basically, all you can do with them is to crunch them up and use them as fillers in concrete. That's about it. Okay, here's the problem. If you've got 4 of these tiles, that's born tiles, and you put a 5th one on top to make contact in the 4 corners, it would work if they were really flat. But of course, nothing in this universe is really flat. And so you tend to have 3 of the 4 corners contacting, and the 4th doesn't make contact because of very slight variations in heights and so on. And so in order to fix this problem, what we had to do is to apply a force to the 5th tile in order to cause them to compress and come into contact. And you rely on the fact that the materials these things are made of are slightly elastic. Okay, well, that kind of works. Here's my version of that system. You can probably see it most at the top right. You can see the pillars, which will be 3D printed there. They're white. You can see a 3 little square circuit boards. The one underneath the crocodile clip, you can see holding it down. That's applying the vertical force I just mentioned. Is an tiny 412 microcontroller, which is a really nice little device, actually, with just 8 beams, which are good also what. And it's shining its little LED to make us learn it's happy to be there. And we can build a more complicated circuit with that. And the test circuit I'm using for this is actually a 2-input neuron from a neural network. Now, I'm not quite sure of the audience that I'm speaking to. Hands up if you have no idea how a neural network works. You're about 20%. Okay. Neural networks are composed of artificial... I'm not going to go into all the stuff about how transformers work and all that sort of nonsense. Just really basically, an artificial neural network is something that mimics the way that neurons in animals work. The way the neurons in your head work, as you're listening to me now, is that they receive inputs, and those inputs are either excitatory or inhibitory. In other words, they cause the thing to want to produce a signal, or they cause the thing not to want to produce a signal. Those are all added up, and if the total comes to bigger than a certain number, they fire. That's it. That's all the neurons in your head do. And this is a circuit for a 2-input neuron. The ones in your head have about 10,000 inputs each. This one's sort of 2 inputs. And it's a kind of weird thing, which, well, I didn't invent it exactly, but it's not the way that most of this research goes. What we've got here is 3 microcontrollers. Our inputs are 2 analog signals that come in on the left there, and we multiply those by weights, so-called. Those are the things that decide how much notice or how little notice the neuron is going to take of this signal. And those weights can be positive or negative. Negative means inhibitory, positive means excitatory. And then we add together the voltages that they produce on their digital analog outputs, and we can add them together just with resistors in exactly the same way as we can have voltages in a operational amplifier acting as an analog computer. In fact, just add them together, produce an average voltage. But of course, if you know how many inputs there are, an average is the same thing as an addition, just multiply it by the number of things you've got. And then they go into a 3rd microcontroller which does something different. It applies what is essentially a step function to this. If the total is bigger than a certain amount, fire, produce an output. If the total is smaller than a certain amount, stay quiet. And one of these is acting as an exciter, and one of these is acting as an inhibitor. And the characteristic of this circuit is shown bottom right here. You get the screen. This is the inhibitor going up there, so more of that means more inhibition. This is the exciter going up here, and more of that means more excitation. And so in this corner here, we've got lots of inhibition and no excitation. We've got a low signal. In this corner up here, we've got lots of excitation and not very much inhibition, so we've got a high signal. And we haven't got a step function, you'll notice. It's actually a smooth-ish surface. The reason for that is that for artificial neural networks, we don't use step functions. We use a thing called a sigmoid function. Reason for that, because we can differentiate it. And that means that we can do the mathematics needed to work out how the network is programmed. Okay, so we've got an artificial neuron that works in a slightly eccentric way. ChatGPT doesn't use loads of resistors to add up numbers for you. Works in a slightly eccentric way, and it does work using this system of the square targets, so that's good. But we've still got this problem that we've got to force the things downwards. You can see a big weight in the top of the bottom left-hand picture, and not really all that clear, but this is a G-cloud. So we had to squash it a bit under some chunks of transparent silicon in order to make the whole confounded thing work. So how do we get around this? Well, we get around it by going in a slightly different direction, which we then have to backtrack from. So let's go off on a slight one, please, Chase. The solution is to make triangles, of course, because a triangle will sit flat however you put it. A three-legged stool always sits on the floor. Four-legged stool will rock unless the floor is protrude very fat and the stool legs are exactly right. So if we put together some triangle elements, we can then arrange them not in a pattern of square pillars, but in a pattern of hexagonal ones. And you can see that bottom left there. They still need to be slightly forced together to give decent contact. And you can see these shiny discs here. Those are actually rare earth magnets. The 3D print had some rare earth magnets embedded in them. And the magnets that I dropped on top of the circuit just hold them down a little bit and stop the circuit from not working when we shake it and so on. And here is a single transistor amplifier, circuit diagram top right. And it's got a gain of -3. The input signal is the one, the yellow trace on the top. It's currently 30 odd kilohertz triangle wave. The output is a little bit simple, a little bit noisy, but then you'd expect a bit of noise from an amplifier, which doesn't have any screening or anything and is put together in this way. So it works. Hey, great. But this problem with triangles. We've got 6 connections per tile, 3 on the top, 3 on the bottom, and that's not enough to do useful things. Why? Because it's really difficult. You can do it, but it's really difficult with just 6 connections per tile to run 2 wires over each other so they don't touch. It's actually quite tricky. You can do it, but it uses a lot of the tiles. And of course, when you're building a circuit, particularly a 3-dimensional circuit, you need to be doing that all the time. And so, unfortunately, this, as I say, is a bit of a wild goose chase. It seemed like a good idea, but it has one very big serious limitation. So back to squares again. Hang on, squares. Lego bricks are square. Let's build some electronic Lego. So this is sort of me causing trouble for the project, really, because I think the other very serious MIT people on the project thought, Lego, hang on, this is a toy. We know it's very serious stuff and was originally intended for architecture and all that. But anyway, because I'm retired and I have 3 jobs, I don't care what people think. So I felt a bit expensive. And I thought I'll reuse Lego. So I made a Lego brick with another 80 tiny 412 in it. On the right, you can see there. And this is indeed the 4 you can see in this picture are 3D printed. In the top of the Lego brick is made in a resin printer. You need that to get a reasonably precise, smooth output. And then the initial one had 4 sides, which are actually pieces of printed circuit board, with the copper facing inwards to form the 4 contacts at the bottom, where the brick plugs into another brick underneath it. And then the 4 studs at the top are just stacks of brass washers held in by a little rivet in each case. There 4 little rivets. And you've got enough room inside, as I say, to put a printed circuit board in it and solder some flying leads to put the whole thing together. This worked, but there wasn't enough compliance in it to get reliable contacts in the corners. So I changed the design slightly to make it more 3D printed. This is a completely 3D printed electronic Lego brick. And what we've got here is the brick. You can see top left there. Same stacks on the studs on the top. But now we've got some phosphor fingers on the inside, which are laser cut. The pattern on the top right there is the laser cut pattern for the fingers, which you bend at right angles. And now we've got these nice fiber lasers, which will cut metal sheet for us. That's really easy to make. And sure, we can start making Lego bricks. What's more, we can parameterize them, write a little Python program for FreeCAD that will make a big brick of any dimensions we want. So here's one that's like 7x4 or something. You just type 7x4 Python program and it makes you a brick and you print it, which is very nice. Bottom right, we've got two bricks. There's standard sort of square brick on the left, like the one we already saw. And then there's a 2-lump brick on the right, which has got two processors in it. And we can start thinking about putting these things together. And again, that all works. There's our original test circuit. There's the result of running this system here. You might think that I'm cheating because look, here are 3 processors here, and now 3, but this is not actually doing anything. This was my test breadboard to see whether that circuit worked. I then left it there, but plugged this circuit in. This is the equivalent to that using the Lego brick system. You can see a couple of these LEDs are lights up when threshold is exceeded. And it produces the same result as you got before, which is good. Well, almost the same result. I actually increased the gradient of the sigmoid function slightly in this one because simulation showed that would produce better results in a real system. Anyway, so and look, real Lego bricks in there, which are very useful because we can use them as scaffolding and structure, and they're pretty easy to obtain. So that's 5 centimeters of each. Okay. And as I say, that works. The downside of this system is that it takes about an afternoon to make a brick. Because it's really fiddly to solder. We've got to use bits of arrow light to put them together, assemble the whole thing and so on. So speed is not, unfortunately, the essence of this. Certainly when it comes to manufacturing. Okay, so here's the next design, and this is where we currently are. Let's make a brick that is still a Lego brick geometrically, but that is entirely made using PCB technology, because we can make PCBs really quickly. And we can also assemble stuff on them really quickly. We have pick and place robots, we have all that sort of stuff. So the basis of it is the 1.6 millimeter thick PCB you can see at the top there, with 8 pillars sticking out of it. These are standard vertical connection pillars that you can get, swage pins they're called, for connecting circuit boards together. The PCB is a rather fancy shape. You can see it's got a hole in it here. This is the hole where the stud will go from the brick underneath. And it's got this little finger sticking out there. That finger actually overlaps with the stud very slightly to force itself against it and make a good electrical contact. And that's actually the weak point of this design. I say weak, I don't mean it snaps off. I mean, it's very difficult to manufacture. Making that thin finger is actually not quite within the standard tolerances that PCBWay and all those people will allow you when you ask your PCBs to create. The other problem with it is they get very confused when you send them a series of edge cuts for the PCB that cut holes in the middle of it as well, and you need those holes to be cut before the through plating is done. That, as I say, causes their production lines all sorts of problems, which cause you all sorts of writing large checks. Anyway, so the structure of the thing actually works very nicely. We've got that at the bottom. Then in the middle, we put the PCB with the active electronics on it. You can see we've got one microcontroller here. It's got an LED, few resistors. There are actually 2 microcontrollers, one on the top, one underneath. So this is a 2-processor brick. And then we put another PCB on the top with, once again, the studs riveted to it, as we had before, because that was quite an effective process to produce these things. And it works. As a Lego brick. There's this having been programmed. You can see that there are 2 pins there which are being moved away from the brick. Those are the 2 programming pins. UPDI, UPI, I can never remember. Anyway, single pin programming of the microcontroller. But we've got 2 of them, so we've got 2 pins. And we can program both microcontrollers in one shot to this thing. Of course, what you're going to do when we start putting these things together with robots is to have the robot gripper program the chip, program the brick as it picks it up, removes it, and puts it down wherever it's going to go. So that works quite nicely. But we still got an interconnection problem. I talked an awful lot about building electronics into these things, but we're going to need to have bricks that wire things together. And in order to do that, we need to have bricks with lots of internal patterns connecting all of the possibilities between the 4 studs at the top and the 4 holes at the bottom. Well, if we're going to have a live active brick of some sort to do that, we're going to have to sacrifice 2 connections for power. So we've got 8 connections in for total, but we're going to have to put some volts in at the bottom or the top or wherever, decide that and stick to it. So we've got 6 connections which we can use to wire everything else up when we use these as part of a larger circuit. And the complete graph of 6 connections per 6 is, of course, 6 choose 2, which I'm sure you can all do in your heads, come out the number 15. There are 15 possible ways of connecting the 6 remaining contacts on a brick in order to route signals through it in any and every possible way that the brick can make. And once again, we can make what's now a new active brick to achieve all this. This is partly where I literally designed the circuit for this before I came here. What this consists of is a brick which rewires itself to allow you to make interconnections between L bricks. It consists of 2 of these rather nice chips, which are MAX 14662s, which are just straightforward single pole, single throw electronic switches. They're analog switches, so they'll switch those voltages, which I mentioned, but they'll also switch digital signals, of course. And we need 15 of them. So 2 of these chips with 8 of those switches in will do us. If we can just fit them inside our Lego brick, you can see the 2 of them there with the pin, with the ground pad, like number 29 on the bottom right. And on the other side of the PCB will be yet another microcontroller, which essentially sets up the pattern that we want when the thing is powered on. Unfortunately, the electronics industry doesn't make things that are the equivalent of field programmable gate arrays, where you can set a load of switches and then have it remember that when the power cycles. It would be really nice to have such a device, and as far as I can tell, none such exist. And these things, nonetheless, work very nicely. Their on resistance is 0.5 ohm, which is very low, and they'll conduct 200 milliamps through each switch. So you can run a watch through one of these switches. You can run a reasonable amount of power through. Now, this at the moment is a design. I haven't made it yet, but I've done some tests on the development boards for being VAX 14662, and it looks as if it's all going to work, so that's kind of nice. So, what have we got? Well, going back to my list of desirable characteristics, we do indeed have one standard shape for everything. It's a Lego brick. We put those sheets, well, Lego bricks do go together in 3D. No soldering. We got solder to put the bricks together, but once the bricks are made, there's no soldering. You build a bigger circuit with them. And there are lots of robots out there that will assemble Lego already in existence. So we've already got robotic schemes for building circuitry using this thing. Scalable, well, we can certainly make small circuits with it. One of the things that I didn't mention is that at this stage, and I'm going to modify what I'm about to say in a moment, but at this stage, we don't care if our GPU is the size of this room. At this stage, later we're going to make it small, but in this stage we're not. We certainly haven't yet built an AI that's designed to modify its successor, but we have made a single neuron for one. Now, just go to the last slide. If you want to get in touch with me, point from that. But to return to this point about size of the electronics constructed using these things, we've got another project running which is working from the bottom up. What do I mean by that? These things are all centimeter scale, what I was talking about. But the other project that's running in parallel is attempting to build electronic devices that assemble themselves at the nanometer and micron scale. And what we do there is we have electronic components that are not in air, but they're floating in a liquid, and they stick themselves together using van der Waals forces so that they organize themselves in the right patterns. And so far we've made a diode, which is good, but we're not at the stage of making a GPU yet either. But nonetheless, a self-assembling piece of electronics at the nanometer scale, of course, you can see would allow one to build objects which are extremely complex, but nonetheless retain an extremely small sphere to close them. And that, we hope, bring the two things together in the middle. Obviously, we can, with the Lego bricks, we can scale those as well. We can do a sort of anti-Duplo and make a half-scale Lego brick and a quarter scale, 8 scale, and so on. And we can keep going down using perhaps different fabrication technologies, like MEMS technologies once we get small. Of course, beyond a certain point, they certainly won't be assemblable by hand, which the Lego bricks currently are. And beyond even a small point, they won't be assemblable by robot either. And that's the point at which we want a Van der Waals system to take over. Okay, that's pretty much all I wanted to say. As I say, it's not about printing electronics, but it's about using 3D printing to make some things that make some electronics. And then back to printed circuits again. Thank you all very much. Please, if anyone's got a question. Forrester Khan's got. Well, I don't want to ask you a question. It's like being a student in front of the lecture. It's like that. Oh, man, close to the back.
My question about the final brings.
Yeah.
Instead of sacrifice, to start.
Yeah.
So, our this year basically we outside
Yeah, that's a possibility.
hours. So do not have certainly had a sacrifice what
Yeah, you might be able to. Slight constraint on that is that you remember the system with the pillars and the square printed circuits that went between the pillars that I showed? Yeah, we had an idea to use the pillars to distribute powers to them, to make an extra connection. But to make reliable connections, you need a white contact when they're put together. Now, you can achieve that, of course, but nonetheless, if you use the edge and just rely on them coming together, that probably wouldn't be all that reliable. But as long as when the edges go together, they do that with a certain amount of appliance in them, what you suggest might well work. Yeah.
And just on that note,
Yeah.
I think it had to be designed their bricks to be slightly smaller and stay safe.
Yes, they do.
So when they actually attach them, it was like things like bend bricks. So you put enough one by two next to each other, spacing gets cut. But that would be using the outside ground grading.
Yeah. It would. I mean, we've got extra connections with bricks program. You can imagine possibly some screen that might use those also to distribute power, maybe. But yes, it'd be nice to try and keep it as clean as possible. I'm not sure whether, I suspect being able to interconnect 6 things in any possible pattern might be enough actually to allow us to go things fairly straightforward. But yes, 15.8 millimeters for a 16 millimeter brick. You're absolutely right. And
2, I think, most elevated questions.
yeah,
So why does it make sense to make a electronically reconfigurable brick that has all of the possible connections rather than just making the thing to replace?
no, there are much more than 15. Remember, you can close more than one switch.
But okay. Other question: have you thought about thermals in all of this? So you had a bunch of microcontrollers.
Yeah,
which will go in flow.
Yes, that's true. The bricks in the end will have holes, and we'll be putting non-polar liquid coolant through the whole thing in order to keep it cool.
Can't get that in doppelganger.
interoperability between different sizes. If you're scaling it down,
Yeah.
your intention to me is that 16 of those is the same as one of these, and to me,
Yeah.
you can indeed plug the whole lot together
Yeah.
as you scale that.
Yeah. Well, you need it. You need a brick with 4 on the bottom and 16 on the top, and that sort of thing in order to do it. You need adapter bricks. But yeah.
Yeah, well, you see in the same way that, say, in logistics, you've got a container where the small containers all fit,
Yes.
etc. Is that what you're thinking of as you scale?
Yeah. Oh, absolutely.
Yeah.
Yes. Sorry, I should have made that clear. But thank you for raising the point, because I should have actually meant.
And can you show me an example of fire strength towards simulated larger scale systems that maybe not be physically possible, but type that be a sounding would you?
Yeah. We've got a design tool that allows us to construct large-scale circuits from schematics. Actually, the design tool was intended for the square bricks made of the square tiles made of PCBs, but of course, functionally, the Lego bricks are identical to those. The design tool allows it. I mean, we built an 8-bit adder with those and so on. It produced. I mean, we made the 8-bit adder in Lego bricks, it would be about so by so by so. So it's not small. But yeah, the answer is yes. We do know that it'll scale in that sense, but we can design things to achieve what we want. But there are all sorts of possible trip-ups between having something that theoretically works in SPICE and something that actually functions when you plug it together with a robot or a human being, which we should doubtless discover in the next few months. So, yeah. Sorry, a bit louder.
When you did post remarks for electronics and like what's already existed in a lot of like and it curious to the fact is some active. Already.
Well, you remember the one I did where the magnets were just supplying the downward force? At that point, we thought, well, shall we use magnets? And I think Apple used to have or still do maybe, have power cables that use magnets. Yeah. We did actually think of that as a way of, and the other thing is that those Apple connectors use things called pogo pins, which are little sprung pins. But we wanted to avoid that as much as possible, simply because they add mechanical complexity. The bit blocks thing that I showed you from Cornell at the start does use exactly that. It doesn't use magnets, but it uses pogo pins. And we wanted to avoid having thousands, millions of springs throughout our system if we can possibly do so. But yeah, we have thought of it. We might return to it. This is a project that's ongoing, and we do finally return to ideas that we previously abandoned.
I wonder if we might do just maybe one more question, and then will you have some time after?
Sure.
Yeah, I have a conversation with you.
Where are we? Half 3. I'm trying to remember what time I changed it. But doubtless my phone will tell me. So yeah, sure, I'll be around outside.
Maybe there's one more back here.
I'm command.
You already to be coupled with our sticky. That's this is weird dashboard. So
No, but the reason is probably because I haven't been building any 500 megahertz circuitry with them. So at the moment, everything we built works, but it is all working at sort of, 100 kilohertz to a megahertz. Those are the sorts of frequencies at which we're currently working. We'll have to see what happens when we clock the clock up a bit.
absolutely fascinating. Ladies and gentlemen, Dr. Adrian Bowyer.